Okay, so this is a continuation of section 3.3, and there are two objectives left that we need to discuss. First one is primes in arithmetic progressions and the famous Burton's theorem. The other objective is to state the prime number theorem, one of the most important theorems in number theory as well as in mathematics. So let me get started by defining officially, okay, formally, what is an arithmetic progression is. Okay, this is a definition. We're going to let A and B to be actually integers, because this is D actually. And we want D not equal to 0, all right, by an arithmetic progression or sometimes we call it or arithmetic sequence. Sequence is an ordered list of this form, an ordered list of numbers of this form. Of the form, we start with A, then A plus D, then A plus 2D, and A plus 3D, and so on. So every time we actually do is we multiply, we add a D to the term to get the next term. So in general, this is A plus KD, and this actually would continue to, indefinitely. All right. So here's what we mean by arithmetic progression. It starts with a number, could be positive, negative, or it could actually be 0. And then we obtain every number from here by adding this D. The order here is important. That's why we put it an ordered list. This is the first, this is the second, and so on. And actually, sometimes we write this one to be the kth term. Actually, we call this is k minus 1, D, okay, and so on. So this is the kth term because this is the first, this is supposed to be the second, okay? So the number in front of the D is 1, and so on. All right, we call A, we call this is the first term of the term of the progression, and we call D, this is the common difference. And this term is given because if you denote the kth term of, or x sub k, all right, to be actually the kth term, which is this, and you take the difference between the term next to this k plus 1 minus xk, you find this is equal to D. And this is true for every k between actually 0 and so on, to infinity, basically. All right? But not equally. So the difference between any two terms going like this. All right. Our objective is to prove a special case of Dirichlet's theorem, okay, which states that under some conditions that we're going to actually state, the arithmetic progression have infinitely many primes, okay? So let me actually state under what are the conditions that need to be satisfied for this statement to be true. Okay? So this is actually theorem 3.7. And we refer to this theorem as Burton's theorem. Burton has many theorems, and this one, since we are in the subject of primes and arithmetic progression, so we don't need to say this is just Burton's theorem for primes in arithmetic progression. This was stated in 1837. And it goes like this. Then let A, B be positive integers that are relatively prime. That greatest common divisor of A, B is equal to 1. Then the arithmetic progression which goes like this: A let me write it let me write it actually in general. First of all, let me put this: A plus B, then A plus 2B, and so on, which means this: A plus actually n minus 1, B, again n start from 1 to infinity, all right, contains infinitely many primes. All right, and it's very important here the word contains, okay? This means that not all the terms, all right, this arithmetic progression are going to be actually primes. In fact, we're going to show this, okay, shortly, that in arithmetic progression, there are, which is an infinite arithmetic progression, there are infinitely many primes as well as there are infinitely many composites, okay? All right, so it contains infinitely many primes. The proof of this theorem actually is way beyond the scope of this course. In fact, the proof of this theorem requires tools from outside of number theory, means that natural numbers and integers. It uses actually methods or tools of complex analysis. Means that calculus basically in the complex numbers. Okay, and it is much actually advanced than just a regular course that you take, such as the course we offered in here called complex variables. It goes beyond actually the scope of even that course. All right, so our objective is to, again, to show, okay, not using this theorem, that there are certain arithmetic progression that contains infinitely many primes. Actually showing it from scratch. We're going to look at a proof that is very, very similar to the proof given by Euclid to prove there are infinitely many primes. Just as an application for this, let's look at this example. Show that there are infinitely many prime numbers that with decimal representation that ends and 999. Okay? So we're going to show that there are infinitely many prime numbers in their decimal representation that ends in 3 nines. So these are the units, the the tenth and the 100 places. All right. And the proof of this, it starts like this. So we're gonna actually apply Dirichlet theorem. We're gonna start with this sequence. Then I'm gonna add 1,000 to this. And then we're going to add another 1,000 to this. Then another 1,000 and so on. Oh, we need another 9 in here and so on. So in other words, this progression that it has its first term is 999 and its difference quotient is 1,000, then n minus 1, again n equal 1 up to infinity. You'll notice that the first term, which is the greatest common divisor of 999 and 1,000 is equal to 1. So by Dirichlet's theorem, this sequence contains infinitely many primes. Now each member of this arithmetic progression actually ends in 999. Of course, the unfortunate thing is we don't know what these primes are, okay? In other words, we have to go through run this because some of the terms of this arithmetic progression is going to be actually composite, and then there are others are primes. But at least in theory, according to this theorem, we know there are infinitely many of them. All right, the special case that I'm going to prove for Dirichlet theorem is theorem 3.6. And it states that there are infinitely many primes of the form 4k plus 3. Okay, you write it down. Okay, so here it is, theorem 3.6. There are infinitely many primes of the form 4k plus 3. As you know, the natural number can be partitioned and be classified into even and odd. The even are multiples of 2, 2k, and the odds are 2k plus 1. We can do also partitioning based on multiples of a 3, 3k, or 3k plus 1, 3k plus 2. 3k plus a 3 is going to be the same as a 3k, right? Or based on 4. And all of this follows actually from the from the division algorithm. So in here we are looking at 4k plus a 3. The other forms of this, 4 numbers using the 4 is 4k, and none of these are primes. 4k plus 1, okay, some of these are primes. 4k plus 2 is not a prime, and 4k plus 3. So we have, this is 4k plus 3. To prove this theorem, we need a very simple lemma. It reads like this. The first thing is the product of 2 or more numbers of the form 4k plus 1 is of the same form. Second is the product of a number of the form 4k plus 1 and a number of the form 4k plus 3 is a number, is the result of the form 4k plus 3. And actually, if you even try this one, which we don't need, the product of two numbers of the form 4k plus 3 is going to be actually of the same form, 4k plus 3. All right, let's go ahead and prove this lemma, and then we can proceed to the proof of the theorem. Lemma is very, very simple. As I said, it's a matter of just doing basic algebra. So here's the proof. So let's assume we have two numbers of the form 4k plus 1, and another one is 4m plus 1. So when I FOIL this, I get 16 km plus 4k plus 4m plus 1. And if I factor out the 4 from the first three terms, I get 4km plus k plus m plus 1. Or if I name this is as k prime, then I get this one is equal 4k prime plus 1. So since it's true for 2, actually we can use math induction to prove that the product of any finite number will be the same. The second part is similar. Let's take 4k plus 1 with a 4m plus 3. Again, foiling this, come up with 16 km plus 12 k plus 4m plus 3. And again, the first three terms has a 4 common factor, and we end up with 3k plus m plus 3, or this is 4k prime plus 3. So it is of this. All right. Now we're going to proceed to prove that there are infinitely many primes of the form 4k plus 3. The proof is a slight modification to the proofs given by Euclid that there are infinitely many primes of all types. Okay? So here it is. First, the proof is going to be by contradiction. So we're going to assume that there are only a finite number of primes of the form k plus 3. Let's say these numbers are starting with p sub 0, it's 3. This corresponds to k equal to 0 in here. Then actually the next one is going to be 7, but I don't want to name these anymore. So I'm going to call them P1, P2, up to P sub r. So we only have r plus 1, actually basically primes, a finite number that is r plus 1 of this one. So we're going to let or define this number q which is going to be 4 multiplied by all the primes, P1, P2, up to P sub r, and I'm going to add a 3 to this. Clearly, the Q is bigger than actually any of the P sub i's, all right, for every I. Starting actually from 0 to I. All right? As you can see, because the Q is bigger than 3, definitely because all these numbers which are bigger than. And these are, we are going to assume they are listed in an increasing order of magnitude, okay? All right, so since the Q is bigger than this for all these primes, means the Q, and these are the only primes, okay? So this implies the Q is a composite number. And it must have a prime factor, all right? Now remember, these are all primes of this form. Now, one other thing, you'll notice that the Q has the form 4k plus 3, okay? So the Q here has this form, 4k plus 3, where the gain here is the product of all these primes. Alright. So since it's composite, this means it must have, this implies the Q must have prime factors. Sorry, more than one prime factor, because you know it is not itself a prime, so it must have more than one prime factor. By the lemma, at least one of the prime factors of the Q must be of the form (4k plus 3). Because if all the prime factors are of the form 4k plus 1, when we multiply them, we're going to come up with the product, actually a number of the form 4k plus 1. But Q is of the form 4k plus 3. So that cannot be the case. All right. And remember, those primes are the 1 which are of that form. Now, first you notice that the 3 does not divide the Q. Because if the 3 divides the Q, and also I have, and the 3 divides the 3, of course, then if I take these two, this implies that the 3 divides combination of the 3 and the Q. Now, the combination I want to take is this. So I want to say that the 3 combination in here is the Q, 3 divides actually 1 times the Q plus minus 1 times the 3. Alright, now if I put in what 1 times the Q, which means this, means the 3 multiplies all of this, 4, P1, P2, and so on, up to the r plus 3. Here we're going to subtract it from this 3, so the 3 cancel out, and we end up with 3, which is a prime, is going to divide the product of all of this. Well, the 3 does not divide 4, definitely, so it must divide one of these primes, so it must equal to one of these primes. Because the 3 itself is a prime. So this implies the 3 is going to equal p sub I. But this is a contradiction because these, they don't have the 3. The 3 was actually singled out as p sub 0. Similarly, actually, none of these primes divides a cube. Okay, so here's the other problem, or lead to a contradiction. So we have p sub I does not divide the cube for every I between 1 and r. Well, let's assume a q sub I. Let's assume that p sub I divides the q for some I. Okay, between 1 and r. Now, we have p sub I divides the product of all the p's. Because p sub I is among these. And also, according to this, or this assumption, and p I divides the q, then p sub I divides a combination of these. P sub I divides combination of the p1 up to pr and the q. Okay, so let's take this combination to be a q minus 4 times these p's. Okay. Okay, so let's go from here. So p sub I for some I divides 4 times p1, p2 up to p sub I. Okay, so we multiply this by 4 and then minus actually, let me put actually q minus this. You take the q. That makes a difference actually. 1 times the q minus 4 p1, p2, so on up to p. But the difference between these is equal to 3. Again, this is a contradiction because this means that p sub I is equal to 3, and this is a contradiction. All right, this is it, which means that and since, again, the primes that are contained in the prime factorization of a cube, because we know this composite must be of the form 4k plus 3, and these are the only ones. Okay, so this means this contradiction implies that there are infinitely many primes of the form 4k plus 6. All right? All right, let's move on to actually, this is a question I asked. Is it possible to find an arithmetic progression as is given in Dirichlet's theorem that contains infinitely many composite numbers? Okay? So the question is, actually the other way around. Let me ask a question like this. Is it possible to find positive integers A and B where the greatest common divisor of A, B is equal 1, such that the arithmetic progression A plus Bn, all right, consists of only prime numbers. We're going to prove that this is not the case. All right? We know that such arithmetic progression contains infinitely many primes. This one, it says, consists of only primes. All right? Since we know it must contain at least one prime, in fact, infinitely many, let us assume that for some integer, actually positive integer, n sub 0, this pair A plus B n sub 0 is a prime. A prime. Again, we know the existence of that because this actual progression has infinite limits. So let's pick one of those. All right? Then I'm going to define, all right? We're going to let n sub k to equal this n sub 0 plus k p, where p is this prime and k equal 1, 2, 3, and so on. So in other words, I'm defining a sequence basically of positive, okay, natural or positive integers. Now I want to look at the, we're going to consider the n to the k's terms or term of the arithmetic progression. Okay, and we can do this one by substituting basically for the this n sub k for n, okay? So we're going to substitute. So we're going to substitute. So this n plus 1 term becomes a plus n sub kb. Okay? And this is equal to a plus, remember n sub k, it is equal n sub 0 plus bk times b. All right, let's work this one out. And we have A plus n sub 0 b. I'm going to distribute the b plus b k b. This is equal p, all right? Because this is the term that actually gives us a prime, and this is p k b, where we can factor out the p, then we have 1 plus k b. All right? And this implies that p divides, all right, this. And these are terms in the arithmetic progression. For every k. And they are all distinct. Okay? It means that these, in fact, these are composite numbers, right? Because they divide, p is a divisor for each one of them. So this means that we have this a plus n sub k b, k equal 1 up to infinity, are all composite numbers in the arithmetic progression. And again, they are all distinct because the in case that we produce these actually are not the same. Remember that the nk is equal n sub 0 plus bk. So we cannot have any two of them are equal. If you said these are equal, you cancel the n sub 0, you cancel the b, and you get k is equal k prime. That's not the case. All right, so there are infinitely many composites. Now, people always try to ask a question in a different way. So we know that there is no arithmetic progression, an infinite arithmetic progression that contains only actually prime numbers. So in general, it would contain infinitely many primes and infinitely many composites. All right? However, in 2008, it was proved that there are finite but arbitrarily long arbitrarily long arithmetic progressions consisting only of primes. Of prime number. Okay? So in the history of mathematics, this is very early. Actually, this is not very old date, 2008. All right, 10 years ago. So this is what we have. There are actually finite but very long, arbitrarily long arithmetic progression that consists entirely of prime numbers. All right? Now, these prime number that is consist of not consecutive, means they just gonna skip some, all right? But however, this has been proved in theory. Now, when it comes to practice, it turns out that the longest sequence or such arithmetic progression progression today, at least to the publication of this book, the 7th edition of Burton's book, is this. And this actually consists of 23 primes, okay? So it's a very big number in here. I don't know if I want to write it down. I will actually. Okay, 2, 1, 1, 3, 8, 3, 7, 6, 0, 3, 9, 7. So this is the first term of the progression, and the common difference is 4, 4, 5, 4, 4, 5, 4, 6, 7, 3, 8, 0, 9, 5, 8, 6, 0, and 10. All right? And the terms that go from n equals 0 up to 22 are all primes. So for these values of n, we all give prime numbers. There are 23 prime numbers is contained in this sequence. As you see, this is not a very actually long or arbitrarily long finite arithmetic progression. This is actually very short. But I say this is in theory, it has been approved, but to produce example, as you can see, this is very big. Now, one of the things that you will notice in here, that the difference quotient actually divides, okay, the difference quotient D for this divides is divisible by every prime, so D is divisible by every prime less than actually 23. All right? So if you look at all the primes, all right, in other words, in the book, they are given the factorization of this. I don't want to write that as well, but the reason I'm stating this because there's a theorem which actually just tells us this, okay? So the difference quotient of, actually the other way around, I'm sorry. The every prime less than 23 is divisible by, I'm sorry, not this way, divisible by the difference quotient. So every prime, this divides by the difference quotient. All right? All right. So let's go ahead and state the next term, which actually say this is what it's supposed to be. All right? So this is the 3.8. And it states that if all the n bigger than 2 terms of the arithmetic progression that is P is a prime, P plus D, P plus 2D, and so on, up to P plus N minus 1D. All right? Are prime numbers then the common difference or common difference D is divisible by every prime the q less than n. That's what we just observed in the previous example. All right, it means that all the n plus n bigger than 2, all right, terms of this arithmetic sequence, they are all primes, okay, all primes, all right, then the common difference is going to be divisible by every prime less than n. Okay, we're going to go ahead and prove this, and the proof is by contradiction. As you see, the argument using the contradiction we use quite often in number theory. Proof by contradiction. So we're going to assume that the q is less than n is a prime, and the q does not divide D. Then we're going to consider the first, the q minus 1, or the q terms actually, sorry, first the q terms in the arithmetic progression. Namely these P, P plus D, and so on. Of course, since Q is less than n, it means it's going to be less than or equal to Q minus n minus 1. So the Qth term is going to be actually Q minus 1 D. All right. I claim that the remainders, all right, that we obtain when we divide each one of these by a q, all right, are different. Here's the claim. The remainders obtained in dividing the first, the first q term. Let me put this as a star in here, okay? Dividing the terms in star. Okay, so the remainder obtained in dividing the terms in star by q are different. We cannot get the same remainder. Okay, so they're going to be all different. this claim, all right? And we're going to do it again by contradiction. So we have a contradiction inside a contradiction, okay? So you have to be careful when you do an argument like this, okay? All right, so let's assume that there are two different terms in a star that leave the same remainder, that leave the same remainder when divided by the cube. We call this, let's say, P plus K D and P plus JD, where the J does not equal to K. So, and in fact, and these are between, okay, actually 0 and Q minus 1, okay? Might put these between 0 and Q minus 1. All right? Without loss of generality, since they are not equal, without loss of generality, let's assume that, let me see which one I wanted to say. The J is a smaller, okay? J is a smaller than K, again, Q minus 1 and 0. All right, so when these leave the same remainder, then by the division algorithm, I can write, I divide these by J, then I can write P plus KD is gonna equal to some Q. We use for this one Q L plus R, and we're gonna assume that P plus JD is equal to QM plus R. So they leave the same remainder, R and R. All right? Well, if I solve for R, both of these, I will end up with P plus, actually write R here. So from here, I get R is equal to P plus KD minus QL. And also the other one, when you solve for R, you get P plus JD minus QL. In other words, we can set these equal to each other. So let's do that. So as you see, I'm not using the contradiction or the assumption that the Q actually divides or does not divide in our argument here. So we're going to put these together, P plus KD minus QL is equal P plus JD minus QL. Okay, let me subtract. I'm going to put this one in this side, and I want to take this into the other side. So we come up with P plus KD minus P plus JD equal, so this one is a QL minus a QM. All right? As you can see, the p's cancel out, and we end up with a multiple of D So this one we can take a d out, and we have k minus j. And in this side we take a q l minus f. So from here I can say that the q actually divides the d k minus g. Okay? Because this one is equal to q multiplied by L minus f. So we have this. Now, since the q does not divide d, all right, then the q must divide k minus j. But this is a contradiction, since the k minus j is actually less than or equal to q minus q minus 1. And which means it's less than a q. It's q minus 1, and this is less than a q. So you cannot have a bigger number divides a smaller number, okay? So this is a contradiction. Which means that this argument that the remainders are the same is not true. So this means that we have all the remainders So therefore, this is the conclusion we get. So therefore, the remainders of dividing each term in star are definite. But what are these remainders? Possible remainders of dividing by q are either 0, if this number divides evenly, or 1, or 2, up to the q minus 1. Okay? Now remember, there are q terms, okay, and there are the q remainders of in here. Alright? Now, one of these remainders must equal to 0. This implies one of the remainders must be 0. And which means that the q is going to actually divide without remainder, 0 remainder, one of the terms. What are the terms? Which is p plus something times d. Okay? For some t. And the t is going to be actually between 0 and the q minus 1. I don't know which term we have, but that's what it is. Okay? It's going to be less than q. All right? This means that this implies this p plus td is composite. But this is a contradiction. This contradicts all the terms are prime. To contradict all the terms are prime. Okay? So all the terms in that arithmetic progression, we say they are prime, so we obtain a contradiction, and again, the contradiction, it means that the net result is therefore we must have the q actually divides d. All right, the last objective on this section is to state and try to understand this one of the most important theorems in number theory as well as in mathematics, which is called the prime number theory. Prime number theory is trying to count, basically, we know that there are infinitely many primes and there are infinitely many composites. The question is, in some sense, which is we have more of, the primes or the composites, okay? Or another way to state this is the following. We need actually a simple function, okay, so the prime number theorem. Or the objective of the prime number theorem is to approximate, is to find the function, simple one, hopefully simple, to approximate the number of primes that are less than or equal a given integer or natural number x. Okay, so we're going to have more say this is more formally. We know that there is no formula that gives us all the primes, all right? We know that. So, in other words, there is also no formula that gives us what's the nth prime, okay? Practical formula that gives us what's the nth prime. It's the 10th, the 100th prime, and so on. You just apply in 100 somehow and to get to 100th prime. There is no such formula, all right? Now, the next thing we could hope for is to find a function that gives us approximately how many primes up to a certain number, all right? To do this, we're going to define a function denoted by pi, all right? And this function actually going to be in, let me see if I want to say from where to where this function. Actually denoted by pi of x, all right, for every x which is belongs to z plus, and is given by this. So its domain is actually the positive integers, and is given by pi of x equal the number of primes less than or equal to x. For example, if I look at what is pi of 1, it is 0. There is no prime less than or equal to 1. Pi of 2 is equal to 1. Pi over 3 is equal to 2. Pi of 5, the primes is 2, 3, and 5, so there is equal to 3, and so on. So let me jump in here. Pi of 20, for example, is equal to 8. Of course, the pi that appears in here has nothing to do with the pi that appears in the formula for the area or circumference of a circle. It is just a Greek letter that has been used for discounting what we call sometimes function for number of primes. That give us the number of primes. In particular, actually, pi of Pn is a very important thing. I of P sub n, where P sub n is the nth prime, is what is equal to? Is this one is equal to, actually is equal to n. All right? Because the nth prime means there are n primes before them. So in some sense, actually, the functions p sub n, which give us the nth prime, and pi are inverses of each other. Because remember that the Pn give us the nth prime, and P of x is give us the number of primes as actually up to n. So if you take the composition of these, you're going to come up with actually, in both cases, n. Okay? So there is, since we discussed this before, and we say there is no formula for P sub n, and these are inverses of each other, then it would be ridiculous to talk about a formula for pi. So what we hope for is just an approximation. All right? Now, so the prime number theory, it just tried to find an approximation for the number of primes. And it first was actually conjectured by, at the same, approximately the same time, by Legendre and Gauss. Okay? Let me put some history here. So the prime number theorem was, or first was conjectured, by Legendre and Gauss independently, actually, about 1793. Legendre said that pi of x, he approximated it to be given by this function, the integral from 2 to x of 1 over the natural log of t dt. And Gauss conjectured that pi of x is approximately equal to x over the natural log of x. Again, what does this mean when we say that these are approximate? It means for large values of x, the number of primes can be counted, can be calculated by calculating this integral, or using a simpler one, which is this function, this simple function, x over the natural log of x. So this was conjectured in 1793. Almost 100 years later, it was proved by two mathematicians again, one German and the other one is, sorry, one is French, I'm sorry, and the other one is Belgium. Okay, so let me put this information down, because we cannot prove, the techniques, the proof of the prime number theory. It needs one whole semester to actually go through the proof, and it uses very sophisticated techniques in complex analysis. And there's another proof was given later on, an elementary proof that doesn't use complex analysis, but still it's very, very lengthy. All right. So here's the proofs. The first proof of the prime number theorem was given again independently in 1896, almost 100 years after it was being proposed by Hadamard. He's a French, and D. Law, I don't know how to pronounce this name, the Poussin. And he's from Belgium. All right. So what they have shown actually in terms of again, actually they use Gauss's approximating function. So they show that that the number of prime less than or equal to x, that phi of x is approximately equal x over the natural log of x for large values of x. Large values of x. So in terms of the language of limits, this is equivalent to say that the limit as x approaches infinity of phi of x over x, the natural log of x, is equal to 1. Well, of course, now with computers and so on, the verification for comparing the number of primes, counting number of primes with the value of this function for different values of x, proved that this estimate, of course, it's a theorem, so it's not a joke. That means it's true. And here is a table to compare the trivial idea, all right, of some of the values in here. So I'm going to have the x here, the number of primes less than or equal to x, and the value of this actually the ratio between those. Or let me put here and then actually x over the natural log of x and the ratios. So phi of x divided by x over natural log of x. All right, let me start with 10, 100. I'm going to skip many, of course. 1,000. This is 10 to the 4th, 10 to the 6th, and 10 to the 9th. Okay? So how many primes less than or equal to 10? There was 4, 125, 168, 229. Then this one is 78498. This one is 50847534. Many primes in here. Now, if you calculate this, you're going to find 4.34, because this one is a function. It's not going to give us whole numbers, but rounded to 2 decimals. So starting with these values. I don't know if you can read those, but 85.74 and so on. And when you, let me move on to the last two here, the last one in here, which is 48254942.43. So if you compare these two values, you're going to see they are very small, very close to each other. And the ratio they give is 1.054. That is very close to 1. Actually, up to, if we go a little more, I guess we can get it up to the 10th digit. All right, so this is the end of section 3.3 and chapter 3. Okay?